What came before the Big Bang? This is a question that must be approached carefully, especially when it comes to how we define the Big Bang itself. If we define the Big Bang as the moment when the universe became incredibly hot and dense, then we have solid observational evidence supporting that state. We can see it when we look out into the cosmos. Our current leading theory suggests that even before this hot, dense phase, something else occurred, a process known as cosmic inflation. Mystery of what existed before the Big Bang has puzzled scientists for decades. As of 2025, there is still no definitive answer. Despite significant progress, no theory has achieved consensus, and claims in popular media about scientists being terrified by the truth remain speculative. There is currently no direct evidence about conditions before the Big Bang. According to the theory of inflation, the universe was once cold and nearly empty before it underwent an extremely rapid expansion. This phase didn't last long, and when it ended in our region of space, the energy that had been driving inflation was released. That energy heated the universe, created particles, and gave rise to everything we see today. This transition marks what we call the Big Bang. So when people ask what came before, they're really asking what sparked this phase of cosmic inflation and why it occurred. One extension of this theory is called eternal inflation. It proposes that while inflation stopped in our region, it continues indefinitely in other parts of the cosmos. You can imagine space stretching over and over again, with inflation ceasing only in isolated pockets. Each of these pockets becomes a universe with its own Big Bang. This leads to a picture of a vast, possibly infinite multiverse, a collection of countless bubble universes, each born in its own Big Bang. While this inflationary multiverse is mathematically consistent, it's still untestable with the tools we have today. This leads us to consider the nature of nothingness. Even the concept of an empty universe, stripped of all matter and energy, doesn't imply true emptiness. Our current understanding tells us that the universe is filled with not just matter and radiation, but also dark matter, neutrinos, and dark energy. Even if we somehow removed all of these, the vacuum of space wouldn't be truly empty. Quantum processes continuously create fluctuations in energy, even in the absence of particles. The universe, it seems, doesn't conform to our idea of absolute nothingness. Remove all energy, and you might expect a cold, featureless void. Yet due to the nature of quantum mechanics, even empty space gives rise to energy fluctuations. The cosmic microwave background CMB reveals radiation left over from the early universe. Its subtle fluctuations help scientists understand conditions before the Big Bang. This evidence suggests that radiation and energy continue to emerge. Even in expanding space that appears empty, can we then say that the universe originated from nothing? The evidence suggests that something always persists. Even if every particle, photon, and quantum fluctuation disappeared, what remains is empty space still influenced by the underlying quantum fields and governed by the laws of physics, according to quantum field theory and measurements of vacuum. Energy, this empty space still possesses a finite non-zero amount of what's called zero-point energy. This is the closest science has come to describing nothing, but it's still something. While we can imagine a deeper level of nothingness, such a state doesn't appear to exist in our universe and can't be recreated in any experiment. As far as science can determine, a state of absolute nothingness doesn't physically exist. Instead, something, however faint, always remains. Still, the deeper why behind this is a question that modern science has yet to answer. Our universe, far from being empty, is bursting with structure. Stars, galaxies, quasars, cosmic rays, and radiation. With newer instruments like advanced telescopes and gravitational wave detectors, scientists are now detecting even more subtle signals, gravitational waves from the early universe. Detailed maps of dark matter and new insights into black holes, both active and dormant. All of this exists in a cosmos that is not static, but constantly evolving. Space itself, what physicists call space-time, is stretching. As the universe expands, distances between objects grow, and light from distant sources stretches, increasing in wavelength and decreasing in energy. This causes the universe to cool over time. In earlier epochs, everything was denser and hotter. In the future, the universe will be colder and more diffuse. Despite this, gravity continues to draw matter together, creating clusters and cosmic webs, as shown in recent large-scale structure surveys. If you've somehow removed every last bit of energy, radiation and matter, space would still remain. It would continue to expand, still shaped by physical laws and filled with quantum fields. This would be the most minimal version of reality we can imagine, yet it would still follow the principles of physics. To a physicist, even this isn't truly nothing. It's the bare scaffolding of the cosmos. Interestingly, current understanding suggests that dark energy believed to behave like a cosmological constant would still be present, even in a universe stripped of everything else. Even if all quantum fields were set to their lowest possible energy states, space would retain a small, non-zero vacuum energy. This zero-point energy means no more work can be extracted, yet it's not quite zero. Theories indicate that even in the far future, as the universe cools and empties, dark energy will dominate, influencing the cosmic fate. Before the hot Big Bang, a different force took center stage: inflation. This phase, dominated by a powerful field energy, expanded the universe far faster than today's dark energy. If inflation is eternal but time is finite, where does the universe truly begin? To unravel this, we must separate three ideas: the hot Big Bang that shaped our universe, the inflationary process that preceded it, and the ultimate origin of everything. Surprisingly, none of these fully answer the question of how the universe truly began. In the early 20th century, major developments laid the groundwork for our understanding. Alexander Friedmann showed through Einstein's general relativity that a universe filled with matter and energy cannot stay static, must expand or contract. Henrietta Leavitt discovered a relationship between the brightness and period of variable stars, enabling distance measurements to far-off galaxies. Vesto Slipher observed redshifts in light from distant galaxies, indicating they were moving away from us. Edwin Hubble and Milton Humason confirmed these galaxies were outside our own, leading to the realization that the universe is expanding. This expansion implies that in the past, space was smaller, and everything within it was denser and hotter. Rewinding the clock far enough, we approach a state of infinite temperature and density. This theoretical state is called a singularity, but modern physics suggests it might simply be a placeholder for a deeper theory we haven't yet discovered. The Big Bang Theory gave rise to 5 key predictions about the early universe. First, the universe should be expanding, confirmed by redshift measurements. Second, the universe started out nearly uniform, with galaxies and structures forming over time. Third, the early universe was too hot for atoms to form, which led to the discovery of the cosmic microwave background. Fourth, nuclear reactions in the hot early universe produced light elements in predicted ratios. Fifth, the high-energy environment made neutrinos vital players in shaping the cosmos, confirmed by modern experiments like DUNE. Despite its successes, the Big Bang Theory alone couldn't explain everything. 3 major puzzles emerged: the horizon problem, flatness problem, and monopole problem. The horizon problem arises because widely separated regions of space have identical temperatures, even though they couldn't have exchanged information. The flatness problem questions why the universe's expansion and gravity are so perfectly balanced. And the monopole problem asks why we don't see exotic relic particles that should have formed early on. Alan Guth proposed a solution in 1980, inflation. This theory posits that the universe went through a phase of exponential expansion before the hot Big Bang. Inflation explains how distant regions could be uniform. They were once close together before inflation spread them apart. It also flattens space by stretching it so much that any curvature becomes negligible. It prevents the formation of problematic relics by limiting the maximum temperature reached after inflation. Inflation then doesn't just solve specific problems. It provides a coherent framework that prepares the universe for the Big Bang. It also presents a powerful alternative to the idea of a singular beginning, suggesting a deeper and more complex origin for our cosmos, one still being unraveled.